So, so we're very happy to have Yael Vinker. Yael is doing her postdoc at MIT now with Antonio Torralba. And previous to that, she did her PhD with Dani Toinor and Arik Shamir at the University. She's been doing a lot of cool stuff. She won several Best Paper Awards at SIGGRAPH, 2 Best Paper Awards and 1 honorable mention. And today she'll be telling us about bridging generative models and visual communication.
Thank you, Tomer. Okay, so thank you all for coming. I'm Yael, and I'm happy to introduce my research. Probably some of you have heard the term generative models, especially recently, but visual communication might be a new term for you, and I'm happy to introduce it today. It is unrelated to communication networks, so expect something else. Let's start with a brief extended intro. Let's see if it works. So yeah, I'm currently a postdoc at MIT. I did my PhD at the University and my master's at the University. I also got a chance to spend some time in Switzerland. I worked at Disney Research and Deep Research. And during my PhD, I also worked at the Google Research. And before all of that, as an undergrad, in addition to computer science, I also studied visual communication design at Bezalel. If you heard about this combined program. So my interest in this field and the way I formulate the problems that I'm working on come from this early interest and passion of mine for the combination of the two. And my research spans computer graphics, computer vision, and machine learning, that is also called AI today. And this map summarizes my work over the past 2 years. So I've been working on algorithms for abstraction. I will explain what it is. Methods for visual exploration through sketches and also in image space. And also parametric generation, which means working with representations that go beyond the pixels across diverse applications like animation, photography, and more. And all of these are under the goal of bridging generative models with visual communication, but let's understand what visual communication actually means. So humans, all of us, we also use visual elements as forms of solving problems, communicate, and thinking. For example, in academia, where we think a lot, we have whiteboards everywhere. And actually, most of us sketch on a daily basis when we teach, when we brainstorm, or when we explain things. And also, some of us have to design some more polished illustrations that help us to communicate better our scientific findings. So these are forms of visual communication when we use visuals to also communicate, explain, and solve problems. And this exists not only in academia, actually these representations are all around us. So all of us use it every day without even noticing. For example, this includes maps, traffic signs, even emojis, and they have long history. So humans have been using and developing these for thousands of years. So these representations span this diverse spectrum, ranging from more exploratory settings to more structured and precise. And in my work, I develop computation systems that can meaningfully engage across this spectrum. You understand what it is? And my work is mostly generative. So this range from models that in the future could actually support this more of early and rough exploration with visuals, for example, models that serve as whiteboard collaborators, to models that can help us to exchange knowledge more efficiently by compressing complex information into very clear visuals. And while this field is generative, probably this maybe feels connected to the recent advancements that we have seen in recent years, where today we can generate very high quality images quite easily from text prompts. This is quite remarkable progress. But maybe you already noticed some differences that in the presentations that we care about in the visual communication, sometimes the goals, the objectives, and the challenges are quite different. For example, often we care about more abstract and simplified representations and non-photorealistic. And it's a hard challenge. How do we abstract content automatically based on meaning and not only, for example, on patch entropy? And also often very abstract representations are the long tail of distribution if you think about all the images we have online. In addition, across the spectrum, often we want representations that can code a structure or complex relationships within objects, and we want them to be editable. And these often go beyond the standard representation of pixels, which also introduce some interesting challenges. And lastly, another question is, how do we support with computational tools more exploratory processes, not only one-shot generation, but when we are not sure what we want to create and we want to explore with models together. So we have these diverse, interesting computational challenges. And back to our map now, with, I hope with a bit of more context. So I've been working across these fields, and today we'll travel along the subset of the box. So we'll start with algorithms for abstraction, in the first part of the talk, and then the second part of the talk, we'll talk about visual exploration, also through the lens of sketches and also through image space, just showing you the diversity of this field. And in most of the questions we'll talk about today, as I will show you, usually we don't really have data sets that model these goals. So we need to, and I will show you that we can actually transfer knowledge from models that were trained for completely different tasks to achieve advancements in this field. Okay, so let's start with the abstraction, which is also where I started my research journey. And the question is how to abstract automatically. And in our first work, Lipasa, we explore the question of computational abstraction through a natural test bed of sketches. So given an input image of some object, our objective, our goal is to automatically generate sketches with gradual levels of abstraction that depict the essence, the important features of that object. And the essence can be defined differently depending on your context. And here in this work specifically, what we wanted to achieve is a combination of what we see, which can be thought of as the geometry and structure of the input object, but also what we know. So we want this to be recognizable as a horse. Under the hypothesis that if we want to abstract, when humans abstract, in order to choose what to highlight and what to omit, maybe we need to have some prior knowledge about the object. We need to know what it is in the first place. And the name of the work, Clipasso, is also inspired by this famous series by Pablo Picasso, where he explores the abstraction of the bull. So I really like this work, and it also inspired, maybe you can see the similarity, it also inspired our work and our hypothesis. Okay, so sketch generation in general is a widely explored task in computer vision and computer graphics. And before Clipasso, we can generally divide the existing works into two categories. So more classical approaches approach this task, aiming to finding meaningful edges, edge maps in an image, only based on changes in pixel intensity, okay? And the thing here is that these algorithms have no notion of semantics. So these filters cannot know they're drawing a horse. And this is why it's hard to achieve a human-like abstraction that way, or high levels of abstraction. And to overcome this later on, data-driven approaches try to generate abstract sketches by learning directly from human-drawn sketches. So if we have access to some big data of, for example, sketches of horses, maybe we can train some generative model that with high probability could generate a new sample that is likely from this distribution. But these methods have some inherent limitation. Once you want to predict some concept that was not seen in training, for example, this alarm clock is clearly out of the solution. So by design, all these methods fail. It's not possible. So all of these methods were restricted to some predefined set of a few hundred categories like cat, dog, and so on. And also naturally, since humans need to draw these things, so usually they depict a very simple content style and low levels of abstraction. And in Clipasso, we asked the question, is it possible to abstract automatically, but without relying directly on such a data? And the inspiration to this objective is from how humans draw. So for example, I draw, and when I draw, if I wanted to draw this horse, I don't need to see millions of sketches of a horse. The way I choose where to put strokes is based on some other experience I have for maybe understanding horses or my vision in general. So the question was, can we mimic that? And in this work, we show that it's possible. And we have 3 key components that makes it possible. So let's see how it works. And of course, feel free to ask anything. Okay, so first is the representation. So how do we even represent the sketch computationally? One common representation is called parametric representation. So note that this is not the pixel image. It's called the parametric representation because the sketch is defined as a list of parameters. In this case, we use cubic beziers. So these are curves that are very well known and useful. Each stroke is defined by 4 control points that decide how the stroke looks like and where it sits on the canvas. Okay? So now our sketch is defined as this list of XY locations on the canvas. Now, while this is a common representation for sketches, in this work specifically, we leverage this explicit control over parameters to also control the level of abstraction. So as I will show you, we will be able to use less strokes in our algorithm to force the algorithm to produce a more abstract sketch. Okay. And the second component of our method is that we don't train any big neural network here. Our only learned parameters will be these control points of the strokes, okay? And we want to learn how to move them around the canvas to form a displacement that depicts our desired concept. And the question is, okay, but how do we learn these displacements, given that we also don't want to use these data sets directly to guide us? So to do that, we will use a pixel-based prior. So let's first understand what it is. So given some parametric representation, we can project it into the pixel space. This mapping is called rendering or rasterization. And today we have very nice and efficient differentiable rasterizers. So this means that if we want, we could backpropagate gradients through this process. So we will start with a randomly initialized set of strokes. So at the beginning, our sketch will look something like that. And then we'll have some guidance term that knows a lot about vision and images that could tell us whether the sketch is similar to the input image or not. And this entire process is differentiable, so we could backpropagate gradients back to update iteratively the parameters of the strokes. So this is an iterative optimization per sketch. Okay, so we optimize the strokes until we converge. Okay, now the question, of course, is the key. What will guide this optimization? And in this talk, we propose to use a vision language model, LIP, that was not trained for this task whatsoever. It's just an encoder. Let's see how it works. So CLIP was developed with OpenAI around 2021, 2022, and it's a very strong model. It is widely explored today. And in CLIP, we have two encoders, a text encoder and an image encoder. And the objective of these networks is to find a shared latent space of images and text. This means, in practice, that we get these two different signals, text and images, and each network will output some vector embeddings such that we can actually define some distance between them, okay, if they lie in the shared latent. This here is the constant signal. Okay. So this is a very interesting vision language objective because we have vision and language together. Today, this might seem trivial, but back at the time, it was pretty new. And with this new objective, the image encoder of CLIP is shown to learn very interesting features. One thing they show in the paper is that this image encoder can encode a semantic meaning of concepts regardless of their appearance. So, for example, with humans can look at all of these images and understand that they contain some cat, even though their pixel statistics is very different from each other. So this is quite amazing, and today we have models that can do that. And maybe you already see that this is quite useful for our task of sketching. So indeed, in this work, we leverage only the image encoder, not the text encoder involved here, to extract meaningful features from the rasterized sketch and the image, okay? So our first objective is that we want to minimize the clip distance between the final embeddings of the sketch and the image, okay, to align the representation such that they lie close to each other. Now remember that this agent space over here is very semantic because the model was trained under the objective of fitting pairs of images and text. So can you maybe guess what might happen if we optimize the stroke parameters using only this objective? So guess. Yeah. Sorry?
Different pose of the pose.
Yeah, this is a close. I guess. The question is, if we optimize the stroke parameters only with this objective, how the sketch might look like. So yeah, what Thomas said is quite enough of the point, but we observe that indeed we converge to some sketch, but you can see that the sketch depicts these horse-like features, like the tail and the legs, but it's not our horse, right? It's a general horse or some kind of horse. And this makes sense if we think about the objective of CLIP. So at the last layer, a clip was trained to fit pairs of images and text. So all of the geometry and the spatial details we are interested in got lost during that encoding. Okay, so to overcome this, we propose to use another objective, which we call L-geometry, defined as the L2 distance between intermediate layer activations. So this is something that is known, especially about convolutional neural networks, that early layers in the network also depict good features of that are more spatial, more related to these changes in pixel intensities like edge map and so on that we have seen in the beginning. Now, specifically here for clip, we have to find specific layers that will fit our goals. So this was a search, but eventually we find two intermediate layers that work really well. And now our final objective is to find the set of source parameters that minimize the weighted sum of L-geometric and L-semantic. Okay, so let's see how this looks like. So here are a few results. So here you can see that in all cases, the strokes start from this randomly initialized set of strokes, and then iteratively they converge to depict the concept. So also it's fun to watch the convergence. And here we can see 4 levels of abstraction, okay? And to achieve to produce this sketch, we applied exactly the same algorithm, and the only change is the number of strokes we started with. And let's look at the last column. So these are sketches generated with only 4 strokes. And we can see that they managed to depict the input quite well, both in terms of geometry and structure, but also semantically, which is quite hard. And note that also the strokes not necessarily lie on the edge map of the image, which was our kind of goal. And in general, this is a hard task. So if I would ask you to draw this horse with only 4 strokes, it's pretty hard, no matter what your drawing skills are. It's a hard cognitive task to choose what's important. And so our algorithm managed to achieve that. And in addition, because we were the first to be able to generate abstract sketches without relying on this set of predefined categories. So we also showed that our method can generate sketches of diverse concepts like the unicorn and origami and so on, simply because by design we were not trained in the way that was usually common. Okay, now in this field, this is kind of a new question, so it's also not trivial to evaluate. So for some people it's fun, I like it, but you also need to kind of invent your evaluation metric. So here specifically to evaluate the success, since we were very organized and we defined the objective as we started, our goal was to achieve a combination of what we see and what we know. So to evaluate this, we defined this as a recognition task. What we know can be thought of as the classification and the category level. For example, if you can recognize this is a cat, so it's good. And what we see can be thought of as a classification or recognition in the instance level. So if you look at this cat, and if you can recognize what was the original input, so it's also a good sign of success. So this was our measurements, and to measure that, we did a user study where we asked people to classify, and indeed you can see that we achieved a very high classification rate, but not surprisingly, as the abstraction level increases, the classification rates goes down. And this makes the, let's say, objective, I would say, under this research question. First, it's interesting to explore where does it break and why. And also, optimally, we would like to develop algorithms that can produce very abstract representations that are also recognizable. So we want this blue bar to be high. And also, interestingly, the confusion rates is not that people were confused between a cat and a dog. So in very abstract levels, maybe you can guess what it is, but this is supposed to be elephant. People just couldn't recognize what this is. So most people under 4 strokes just thought it was nothing, which is also interesting because this might be different from the mistake rates of humans abstraction. Okay. Now, to more thoroughly evaluate this, after this work, we also collaborated with a team from Stanford, the Cog2 Labs, and they are interested in sketches from the cognitive science perspective, exploring how and why people abstract. So together, we wanted to develop some more thorough evaluation, comparing machine-grown abstraction, which was classical at the time, and the human law abstraction. So we collected a big data set of asking people to draw under different time constraints. And then we did some interesting analysis comparing between the two. Eventually, we found an interesting thing. It's just a test from that. First, you can see the recognition patterns are quite similar. Okay, so also abstract sketches of humans are not very well recognized. And interestingly, so we chose clip. Of course, we tried, for example, the VGT, which was back at the time, but we didn't try other methods to guide our optimization process. And here, more thoroughly, we tried to explore different models to classify the sketches. And indeed, we observed that clip was more successful in sketch classification, which kind of also confirmed our choice of clip. Okay, great. So in terms of the impact of this work, so people in the community really liked ClipPasso. Also, I think the idea of the abstraction and the results. So we received the test award, the SIGGRAPH 2022, and also it was widely covered in the news and blogs and so on. And artistically, the appearance was pretty nice, and because it's parametric, you can also print it with a plotter. So people printed it. I also printed it. It looks nice. And also, many people actually used our work, even though sketch abstraction was not back at the time the most trendy task. But you can see that we had thousands of fans to our demo and so on, and people used it in surprising ways. For example, using to generate data sets to solve the task, and also to inspire the new research questions. So this was quite surprisingly nice. And in general, our technical components are widely deployed until today across diverse applications and graphics. Do you have any questions before we move to the? Oops, I forgot to say. We also have an evolving community, interdisciplinary folks that are interested in drawing and sketching from the computational and cognitive perspective, and we are now building this community, and actually a lot of people came to our recent workshop, and we will organize another one next SIGGRAPH. Okay, so do you have any questions so far?
The recognition rates you showed are by humans or by classifiers?
So what I showed is by humans. We also did a classification, but we don't really have very strong sketch classifiers in general. So we had to use clip, but clip also was used to optimize. So we had to support, so clip alone is not enough. We also got pretty similar rates with clip, but we had to support that with human study. Yeah.
The geometric loss is a little more like engineered. You have many models. Do you have a overreaching principle how to find it with a new clip-like model?
Yeah, it's a great question. I can also take this opportunity to show you actually how it looks like, because it's interesting. So I have a slide on the, let me find it. Yeah, so so there are not so many layers. In the ResNet, there are 5, and in the VAT, there are 12. So we actually just did it manually. We tried to optimize with each individual layers and combination of the two. And eventually, I just chose it manually based on my own taste, which is good apparently. But there is no a method to choose that automatically that I'm aware of. But I think this is also a research question, like what is the objective to choose it? How do you measure? Because we don't really have very solid metrics, so it's hard to do that only with like automatically. So specifically, we didn't use Dino in this work, so we didn't compare. Yeah, but this was a follow-up work that we just wanted to more thoroughly evaluate. So we also compared to Dino as a classifier. But in this work, at some point at the beginning, I did try with Dino, but it didn't last for long. I just used clip. It worked pretty well. Yeah.
It's different for each sketch, human sketch, or just when we can have one sketch.
So in this algorithm, it is fixed. So we chose specific 2 layers, which was layer 3 and 4 for all the sketches. But if this interests you, so in a later work that's called ClipPasso, we actually used different layers to achieve different types of abstraction, which is pretty cool. So it's interesting. I think the effect of different layers can also reveal something about what the layers has learned, but also be used for different types of abstraction. Okay, great. So thank you for all the questions. And now, yeah. Okay, great. So we covered the algorithms for abstraction. It's a whole world. There's a lot to do there. But now I also want to talk a bit about visual exploration. We'll start again with sketches briefly, And then we'll also talk about the image space. Okay, so what is visual exploration? Okay, so probably all of you have played with these models that we have recently, text-to-image models. These are great, but they kind of are designed to support a very specific stage of creation, where ideas are already fully formed. We have a very clear vision of what we want to create, and the assumption is that we can represent it with a prompt and generate an image. So someone decided that like this is how it works. But in fact, in visual creation, there is a whole process of exploring before we know what we want to create. And these involve common practices, especially in the visual domain, of seeking inspiration, sketching a lot, exploring ideas, all of that before we are very clear about what is it that we want to create. And this is true about any creative process, also in research that you all do. It's not that we have an idea for a paper and tomorrow we write the paper. Sometimes it can take years of exploring, inspiration, which is reading papers, and so on, okay? So in my work, I'm also interested in supporting these early stages of exploration, and I want to show you a few examples of sketching and what does it mean. Okay, so sketching, beyond being a great testbed for abstraction, it's also a very great tool for exploration. So across disciplines, of course in design, but not only, often the first thing that we do is to sketch. Also when we do research, for example, and this is an exploratory process. We don't know where we end up with, right? So recently I'm interested in thinking about whether someday machines could also participate and maybe even autonomously take part in this more exploratory process that is done through these more abstract representations. So there are many ways to think, how do we get there? One thing that I'm interested in recently is modeling sketching as a process. So not only necessarily we care about the final result. So in Clipasso, we optimize all the strokes together. The final sketch is plausible, but the way to get there is not similar to how humans actually draw and think with sketches. So now my goal is to also produce sketches where the process is important. And again, we have the same problem where we don't really have data sets of such a thing. So we need to use some priors, some other models that will guide us on how to do that. So in Clip, we use Clipasso, we use Clip, which was trained on static images, and now we are looking for more temporal priors. So I want to briefly introduce two recent works in that direction, where we use two different priors. So first, language models, probably all of you played with them. They are very strong, and while they cannot really draw directly, apparently they can produce very detailed commands on how to draw, even in sorted by order of importance. And also they can produce visuals or draw with code. For example, they're really good with producing graphs. So we will use that. And more recently in another work, we explored video models. So video models are more naturally temporal and visual. And this is a result if we prompt Sora really hard to produce a sketching process. So this looks maybe similar, but of course it's not what we want, but this will be useful. So let's see how we use these two priors to produce a bunch of sketches. And so in sketch engine, what we do is that we take an LLM, a language model, and we force it to produce commands in some sketching which we designed, telling us how to draw sequentially. Okay, so these commands are sorted, and they are designed in a way that we can easily parse them into cubic Bezier curves, getting this sequence. And I will show you how it looks in a moment. And with the video work, we present sketches completely differently, more like a video. So now a sketch sequence is a sequence of pixel frames. And we show that with the future fine-tuning on a very small set of high-quality examples, we can actually distill a video model to output videos that look only like that, and leverage its existing prior to generalize to other classes. And interestingly, these two different priors produce very different sketches that also may tell something about what they have learned. Okay, so language models, we know that they are very knowledgeable. They were trained probably on the entire internet, and therefore they can also draw very complex concepts. And so here is an example of the double-slit experiment. And of course, to be able to draw that, you need to know what it is. So this is a big advantage of using language models for this task. They are very versatile. You can use them for diverse tasks, even challenging ones. And on the other hand, video models are not there yet in terms of their knowledge. So even if we give very precise prompts or commands on what to draw, the video model simply does not know what this is, and this is why we get a sketch that is incorrect. However, on the other hand, there are also big advantages to the video model. So once we want to generate, to draw something that is more simple, like animals, for example, so you can see that this elephant might be correct semantically, but it's very, very simple. It's as if each stroke corresponds to a semantic part, and we can think of this as more like how children draw. And this becomes more apparent with more concepts. You can see that it's not very professionally looking. And specifically in our work, this was our upper limit. So we tried a lot to achieve higher level of details and better appearance. We just couldn't. So it seems like maybe there is an upper limit for the ability of language models in these domains. And video models, by nature, were trained on a visual signal. So the visual power is stronger. And this is also apparent in the type of sketches that we managed to achieve. They look more professional. It's also easier to adjust the quality of our method based on this small set of examples. So they're more versatile in terms of the style we can achieve. And this is a trade-off, an interesting trade-off. Let's see some more examples to exemplify that. Okay, so again, we can see we managed to achieve sequential sketching. By the way, these are the first works that managed to do that without being restricted to predefined classes. And you can see again the patterns that when it comes to animals and so on, the quality is very simple, but when we need correctness, so for example, in pendulum motion, this is much more correct than this one that just has the appearance, but of course, it's not really what we wanted. And this is just the beginning of this idea. So we still have a long path until we get to models that could actually draw and communicate with us through visual representations. Hopefully in the future, in the same level that today we can talk in English freely with ChatGPT. Maybe in the future we could also talk with models with the language of sketches, which is very natural for many of us and also in many disciplines. And I will show you in my future work how I plan also to get there. We have like 2 minutes for questions if you want. Okay, great. So we talked a lot about sketches. It has been a major part of my work. But I'm also working in image space on actually pixel images, but sometimes under different objectives. So I want to show you another work around visual exploration, but this time beyond the sketches. Okay. So remember that we said that there are many things that we do before we know what we want to do. And when we create something that is visual, naturally, this exploration is in the visual space, not necessarily only through text prompts. And a few examples of how this looks like. So in fact, a lot of designs and human-made creations that we see around us are usually inspired by others' work or sometimes very commonly concepts in nature. And so I really like this design in general, but if we look at this example, we can see that first, if we look at these two, probably most of us can see the connection, right? But it's not like what was the part of inspiration that the designer took from this sea creature. But first, it's not trivial to describe it with words. Maybe we can find a huge font, but it will be not natural and maybe hard. Secondly, it's not trivial to do that connection. So it's not trivial to look at something, even if it's very interesting, find an interesting aspect of it, and create something new and original based on it. This is hard. You need to be very experienced to do that well. So a question is how can we support these more exploratory processes of inspiration and exploration with generative models? So let's assume we have some image of some concept, some objects that we like, that inspires us. Maybe I like the drawing and I want to start exploring. I don't know what I want to create yet. So in our work for the inspiration tree, because it provides a tree, we provide an automatic method to support this kind of more exploratory processes. So first, what we do is that given an image of your interesting concept, we automatically decompose it into its visual aspects that sit in this hierarchical binary tree structure. Now, each node in this tree is actually a vector that corresponds to a new world that can be further used for exploration. So let's assume now you have a visual image of some hierarchy and some interesting stuff, so maybe you like something. And now you can actually use this as a visual entity to start further exploring ideas with text-to-image models. So maybe you want to explore how a chair would look like inspired by this, or a cat drawing, and so on. And you can even explore variations of your own concept. For example, you can exclude the V3 from the tree and reconstruct it to the root and get your object, but without the texture. So this is a visual exploration space. Okay, now let's see how do we implement that. So first, in general, this is how task in computer vision, I would say in general, given some image, how automatically do you decompose it into its visual elements? It's not just partially cut the bear, for example. So to do that, we will use the existing files of text-to-image diffusion models. Sorry. Okay. So in a nutshell, what these models are. So text-to-image diffusion models are generative models. These are new ones before. Often it's called the epsilon theta. And in general, this model is trained to generate new images by mapping samples from a known distribution, usually Gaussian distribution, to the approximation of the data distribution. And this process today can be also conditioned on a text prompt. Now, how this condition is performed in high level, given some text prompt, first you need to encode it into some vector representation. We can think as if each vector here corresponds to a word, or it's also called a token in the sentence. And these vectors lie in what we call a textual latent space. Okay. So with this, we can generate new images that are described by sentences in English. But questions that people asked for me also is, but what if I want the model to generate images of my own concept? Maybe I can find a very long prompt that describes the specific concept, but this might first not be possible. Second, it's hard. And third, it kind of block our visual exploration that we want to support. And okay, so in fact, very smart researchers who are also my friends from Tel Aviv University showed that you can actually inject visual concepts represented as images into this textual latent space, such that now you have a vector that lies in this latent space that is linked to some new word, some new token, such that every time you will condition generation on the sentence without changing this network at all, this is completely proven, and the network will generate images of your own concept. This is called personalization, and specifically this one is called textual inversion or personalization because we inverted the concept into the textual latent space. Okay, so this is great. It is widely used, and it will also help us to construct our tree because we want to have this quality where visual concepts are described as one unit and not very long forms. Okay, but note that in textual inversion, to find this vector, this involves some optimization. In fact, the way it works in high level is that you need to start somewhere. Usually it's recommended to start with a concept that is somewhat close to your own concept, like a coaster in our case. And then it's some kind of iterative optimization and search in this latent space based on some distance between the generated image and your own concept, okay? So this means that we need supervision here of the concept, obviously. But in our case, first we don't just want to find one token per image. We want to find this hierarchical tree structure. And also we don't have supervision because we don't, not only that we don't know what these images are, we also don't want to force anything about their nature because we want the tree to inspire us. So this is hard. How do we do that? And even though it's a very hard problem, in this work we show that the algorithm is quite simple and elegant. Okay, so first to achieve that, we'll do that iteratively step by step. So let's assume we managed to decompose the parent node. This will give us supervision for the next level. So we create our own supervision. If we decompose the first level, we can create images, which will guide us on the decomposition of the second level, and so on. So this means that our problem now becomes, how do you decompose one level? And now let's see how do we do that. So we will learn to decompose by actually learning to compose. So we will use the only supervision that we have, which is each time the parent node. And our objective is to find two vectors in this latent space that together depict the parent node, okay? Which is translated into, if we condition the generation on the sentence containing these two consecutive words, we want eventually the model to generate an image depicting our own concept. And this will be an iterative optimization. Where should we start this optimization? So we find that a good starting point would be with a general concept, like the word object, which works really well. So in practice, we initialize these two vectors in the latent space with the embeddings of the word object. So they are initialized exactly to be the same. So at first, if we generate images with this word, with this vector, we'll just get some images of objects. And then this will be an iterative optimization process following the process proposed in textual inversion, but this time with a modified term. Instead of optimizing on a single word, all we do is optimizing on two consecutive words. So with this optimization, indeed, when they are optimized together, after a few steps, actually like a lot of steps, eventually this converges to depict the concept that we want. But the question is, okay, under the optimization, these two words always live together. They don't live separately. So how do they look like separated? Let's see. Okay, so in the first step, as we said, it's just simply an object and an object. And the key insight of this work is that we find that when we optimize them like that, as two consecutive words, the information tends to split naturally. Thanks to the existing prior of the model. The model is not used to see two consecutive words that are the same. So they always tend to diverge from each other. And not only that they diverge from each other, eventually, in most cases, they converge to depict different aspects. So there's a natural split of information here that only happens thanks to the prior of the model without using any such data sets whatsoever. Okay, but note that this perfect separation is not always guaranteed. So often we find that even though the two vectors always diverge from each other, sometimes they converge to some incoherent concepts or vectors in this latent space. This means that if we will use them to generate images, we'll get a bunch of random images. And we have an automatic way to filter that thanks to clip. So we simply generate a bunch of images and code them with clip. And then to recognize if this is a random or like incoherent set, if the clip similarity of all the pairs is low, this means that this just depicts a random concept and vice versa. So we have a way to filter that. And then in around half of the cases, we converge to very nice separations naturally. Okay, great. So now I showed you how do we decompose one level. And then as I said, simply to build a tree, we just repeat this process. And now we have this visual exploration that defines the tree. So we can visually observe different aspects and use them further to generate concepts, a lot of concepts like house, chair, dress, and so on. And you can see that the information split works pretty well with this implicit approach. Let's see another tree. So I like this tree in particular. This cat is actually part of a famous benchmark in this field. So we can see in the first level that we got the colorful stripes and the blue cat-like sculpture. But in the next level, the interesting things start to happen, some surprising aspects, which was our goal. So for example, if you look at this time, at first, it's not 100% clear what is the connection to the cat. But if we observe closely, for me, for example, I thought it's the tail. Antonio, for example, thought it was the stripes. And this is kind of a magic where when concepts are kind of incomplete or not 100% clear, it invites interpretation. And then more synergically, we work with the model to create something. So this could inspire us to use this structure to create something new. And another nice thing about the method is that easily we can combine sub-aspects from different trees, because these are just new words in the dictionary, so we can just simply use them together. So here, for example, we took the blue cat sculpture from the cat and the stone surface of the Buddha, and we can easily combine it together to get these hybrids and nice combinations that can further help us to explore ideas. Any questions about? Oh, okay. Okay, so also this work kind of drew some attention from the community. We just did the paper, the Sea of Asia, And this whole idea of decomposing visual concepts with these different words more implicitly also inspired follow-up works. And the whole concept of using the field space for more exploratory settings, not necessarily one-shot generation, it also inspired some follow-up works. And in addition, I saw recently, because I presented it to some friends, and then they knew this work because they learned about it in the course. So it was also taught in the Stanford course last year. So it drew some attention, gladly. Okay, great. So we covered the map, and we saw today that across these unique tasks that often we don't really have data sets to solve them directly, with recent advancements of models, large models that were trained for other tasks, we can actually achieve quite advancements in these questions that maybe were not possible before because of this data bottleneck. And also there is a whole part, if you notice from the map, that we didn't cover today. Also very cool work if you want to talk about it later. So I also work a lot on parametric representations, mostly vector graphics, showing that, again, we can use piles of models to achieve tasks that are new and unique and were not possible before, including generative typography, which is cool, and also animating static sketches with prior video models. So it's a whole world of how we generate content in vector graphics with priors from pixels, where we do have a lot of data. Great, and we have enough time for future work. So I want to tell you also what I want to do next. So in fact, each of these topics often ask some new questions, and as the model priors advance, it also enables us to explore harder questions and further develop these objectives. And this is something that I'm doing. But note that in each of these works, we use kind of a different prior. And while this worked very well, and there was hope that the priors will just become better and we will be able to do anything, it seems like maybe it also gets into some upper limit. For example, after I worked a bit with language models, who seems to be just magical and work for everything, I found that they are very limited in the space of visual communication. And video models, on the other hand, are suboptimal. So this raises the question on how and if we can develop more unified priors. Can we define the priors ourselves that will more naturally fit the tasks in visual communication? Okay. So in the longer term, I am interested in exploring this, and my current thought is inspired by humans. So in fact, the fact that we use visual communication is potentially not random. The fact that some of you draw a graph to solve a problem or to better organize information can be thought of as some kind of externalization of our internal representation. So something in the spatial arrangement or visual signals help us maybe to solve problems and explain. And there is literature in cognitive science to support this hypothesis. And also, some of us can testify that we are visual thinkers. For example, I consider myself to be a visual thinker. It's quite common. And I want to ask whether we can develop models that are also these more visual thinkers, meaning that we don't just force them to draw because of our representation. They have some internal incentive to solve problems that way. So there are many ways to think about how to do that. It's a kind of a broader question. I had a few future directions that I want to explore. One way would be to directly learn from human visual thinking. So actually, we as humans think a lot, especially in academia when we solve problems with visuals, but this information is not usually recorded. So one thing to do is to record this information. And the second question is, what is the correct or most useful representation for that? So today, most models are trained on vision and language, where the visual part is the final solution, usually the final result, which doesn't show us the process. And the textual part does show us the process. Maybe this has led to what we see today, but it's textual. So I believe that if we also incorporate the process itself, not only the final result, but how did we get there in a visual representation, this might help us to achieve this goal. And I'm a big believer in the parametric representation for that because it is more compact and it's also easier to verify its correctness. So this would be one direction. Another more exploratory direction would be also inspired from cognitive science research, where there is an hypothesis that the reason that we think spatially and visually is because we live in a 3D space and we have eyes, so we see. And a lot of the time we do some actions in space, we navigate, we move, we touch things, we point, and this might be the reason that eventually we use these graphical representations. So it would be also interesting to further explore this connection between the two and maybe add this additional modality of moving in space and actions in space. Okay. And then another interesting thing we can do with such models in the future. So let's assume that we reach to a point where we have models that can draw, like we have models today that can speak. But it's not the end of the story. So once we had models that can speak, suddenly they are everywhere. We use them for science and for many use cases. And I think it would be interesting to explore how models that can draw can be used to ask interesting questions across disciplines. So one interesting thing is to start using them as simulations to solve a task together, some tasks that have some literature in cognitive science. And maybe together they could develop abstraction or some language or some new representation. Okay, and just to sum up, it's the end of the project. So I think that this time is very exciting for this field. So when I started my PhD, it was kind of new and not we were uncertain on where can it go. And I think that today everything moves so fast. And I think that especially given the recent advancement in language models, where it seems that maybe they have reached some upper limit, I think it's interesting to start exploring what can we do with models that could use these abstract representations like us to solve problems and communicate. And I really believe that it can change the diverse fields and diverse applications once we have models that can do such complex tasks, also in the visual world. Yeah, so thank you for listening. Questions?
Yes, I have a question.
Goes well. Okay, yes, online.
No, regarding the concept tree breakdown, it would seem that sometimes the concepts get entangled. Is there have you tried or have you looked into maybe trying to enforce them to be orthogonal in a sense?
Yeah, that's a very good question. So indeed, we tried to force orthogonality during training. We also tried to force different relationships, like making them be the sum of the parent node and so on. At the end, nothing of these worked. What worked best was simply using them as consecutive words in a sentence. And this kind of gave us this information split. But the information split is not necessarily perfect. It's not necessarily completely disentangled, but yeah.
Thank you.
Okay. Yeah.
In the first word, you said that the level of abstraction is dictated by the number of strokes, right? So, but the number of points that control each stroke is fixed, right?
Yeah. Right.
So, I think that is a very different.
Yeah, so in the paper, we also eventually we can support the curves that the differentiable rasterizer library supports, and they do support curves with other complexities. So we do show, for example, results with using only linear lines or quadratic curves and so on. And at the end, the thing is that, yeah, so you can use different primitives, and it's definitely interesting. The thing is that this aspect is not learnable. It's not differentiable, so it would also be interesting, in fact, to generally learn also the complexity of the curve to fit different problems. But this is not something that we support because it's not differentiable with this library.